Hello everyone, welcome to QBite. In today's video, we're going to talk about one of the simplest but most important math ideas behind quantum computing, vectors. Don't worry, we are not going into anything scary or complicated. We are just building the foundation slowly, step by step. By the end of this video, you will clearly understand what a vector is, why we use vectors to represent classical bits, how the positions inside a vector relate to 0 and 1, and what the norm of a vector means. So let's begin. What is a vector? For our purpose, think of a vector as a little container that holds a list of numbers. That's it. If the vector has two numbers, you can imagine it like a top position and a bottom position. So a two-number vector is simply like A at top and B at bottom. Nothing more. Why do we use two-number vectors for bits? A classical bit has two possible values. It can be 0 or it can be on. So a vector with two positions is perfect. It gives us two slots where we can place information. S position in the vector corresponds to a bit value. Top position represents the value 0 and bottom position represents the value on. You can also think it as two indicator lamps. If the top lamp lights up, then the bit is 0, and if the bottom lamp lights up, then the bit is on. Now, how do we represent classical bits using vectors? The rule is extremely simple. To represent a bit, put a 1 in the position that matches the bit value and put 0 in the other positions. So, to represent the bit 0, we put on at top position, or you can say at position 0, and we put 0 at the bottom position, or you can say at first position. Similarly, to represent the bit on, we put on in the bottom position and we put 0 at the top position. These two vectors are standard classical representations for 0 and on. Later in quantum computing, this will become our basis states. Now let's talk about something very important, the norm of a vector. The norm simply measures the length or size of a vector. If we have a vector A, B, the norm is calculated using the Pythagorean idea of distance from the origin. Now let's write it. Norm equal root A minus 0 whole square plus B minus 0 whole square. But you may have question, why do we subtract 0? Because the vector goes from the origin 0, 0 to the point AB. So the distance formula is root A minus 0 whole square plus B minus 0 whole square, which simplifies to root A square plus B square. Now let's apply this to our bit vectors. We have the vector for bit 0 is on 0. So in this case, A equal 1 and B equal 0. So the norm is root 1 minus 0 whole square plus 0 minus 0 whole square, which simplifies to on. Now similarly calculate the norm for bit on. The vector for bit on is 0, on. So in this case, A equals 0 and B equals on. Then the norm is root 0 minus 0 whole square plus on minus 0 whole square, which again simplifies to on. So both bit vectors have a norm of 1, meaning they are clean, normalized and perfect for representing states. This norm equals 1 idea became extremely important later when we move into pure quantum states. But for today, this is enough. Now that you understand what vectors are and how they represent classical bits, let's go to the lab and code using NumPy. Alright, let's switch to the practical part and write some code in Google Colab. In your notebook, type import NumPy as np. NumPy is the library we'll use for vectors, matrices and all kind of linear algebra. Now create the vector for classical bit 0. Remember the rule, put on in position 0 and put 0 in position on. So we write like bit 0 equals np.array on, 0. Now you can see the vector representation of classical bit 0. Similarly, let's create the vector for classical bit on. Now the on goes in position on and 0 goes in position 0, and this gives the vector representation of classical bit on. Now let's compute the norm of S vectors. Before you use NumPy's built-in function, we are going to compute the norm manually using the exact math formula we talked about. Norm equal root a square plus b square. This helps you understand what the norm really is, just a distance calculation. So in both cases, we get the norm equal 1, exactly what we expected from the formula. Now compute the norm with NumPy's built-in function. To compute the norm, we will use np.lineals.norm. Again, this gives the same result. Both norms are on. You can also verify the bit value by checking the position of the on. This confirms that for bit 0, on is in index 0, and for bit on, the 1 is in index on. So that's the whole lab for today. We created vectors for classical bits, printed them, computed their norms manually using the full distance formula, checked the norms using NumPy's built-in method, and finally confirmed how the vectors on position directly encodes the bit value. And that's all for today. In the next video, we'll discuss about matrices. Make sure you subscribe the channel and share the videos with your friends who are also interested. See you in the next video. Until then, happy quantum computing.